Welcome to a journey through the shadows of mathematics. Tonight, we explore the forbidden territories of human knowledge, those mathematical truths so profound, so unsettling, that they challenge the very foundations of reality itself. You are about to encounter concepts that have driven brilliant minds to madness, theories that suggest our universe might be nothing more than an elaborate mathematical illusion, and proofs that demonstrate the fundamental incompleteness of all knowledge. These are the mathematical secrets that control your life in ways you've never imagined. The hidden equations that govern consciousness, time, infinity, and existence itself. As you drift towards sleep, let these impossible truths wash over you like waves against the shore of comprehension. But be warned, once you've glimpsed these forbidden mathematical landscapes, you may never see reality quite the same way again. The comfortable illusions of everyday existence will begin to crack, revealing the strange mathematical machinery that operates beneath the surface of everything you think you know. So close your eyes, relax your mind, and prepare to descend into the beautiful, terrifying depths of forbidden mathematics. Our journey begins in the early 20th century with a young Austrian mathematician named Kurt Gödel. Picture him, thin, nervous, brilliant beyond measure, working late into the night in the libraries of Vienna, about to shatter humanity's greatest dream. For over 2,000 years, mathematicians had believed in the possibility of absolute knowledge. They dreamed of a complete system, a perfect mathematical framework that could prove every true statement, answer every question, resolve every paradox. Mathematics was supposed to be humanity's glimpse of divine perfection, a realm of absolute certainty in an uncertain world. Gödel destroyed that dream forever. In 1931, he published what would become known as the incompleteness theorems, two mathematical proofs so devastating that they changed our understanding of knowledge itself. These theorems revealed something horrifying about the nature of truth: that any mathematical system complex enough to include basic arithmetic must contain statements that are true, but unprovable. Imagine, if you will, a library containing every mathematical truth. Gödel proved that this library must contain books written in a language that cannot be translated by any method within the library itself. There are truths that exist, truths that are absolutely certain, but which can never be proven using the tools of mathematics. The first incompleteness theorem states this precisely: in any consistent formal system that is capable of expressing basic arithmetic, there exist statements that are true, but cannot be proven within that system. Think about what this means. There are mathematical facts as real as 2 + 2 = 4, but which will forever remain beyond our ability to demonstrate. But Gödel's second theorem cuts even deeper. It reveals that no mathematical system can prove its own consistency. The very foundation upon which all mathematical knowledge rests cannot validate itself. We build towering structures of mathematical truth upon ground that we can never prove is solid. This is the mathematical equivalent of being unable to lift yourself by pulling on your own bootstraps. Every mathematical system powerful enough to be interesting contains within itself the seeds of its own unknowability. We are trapped within formal systems that cannot guarantee their own reliability. Gödel achieved this through an ingenious method of self-reference. He created mathematical statements that talk about themselves, sentences that say, "I cannot be proven." If such a statement could be proven, it would be false. If it cannot be proven, then it is true, but unprovable. This creates an inescapable logical paradox that reveals the fundamental incompleteness of all mathematical knowledge. But Gödel's work was built upon an even earlier mathematical catastrophe: Russell's paradox, discovered by Bertrand Russell in 1901. Russell found a simple question that broke mathematics itself. Does the set of all sets that do not contain themselves contain itself? This sounds abstract, but Russell illustrated it with a vivid example. Imagine a town with exactly one barber, and this barber shaves all and only those people who do not shave themselves. Who shaves the barber? If he shaves himself, then he belongs to the group of people who shave themselves. But he's only supposed to shave people who don't shave themselves. If he doesn't shave himself, then he belongs to the group of people who don't shave themselves, which means he must shave himself. This paradox revealed that naive set theory, the foundation of all mathematics, was contradictory. The mathematical universe that mathematicians thought they inhabited was actually impossible. Everything built upon set theory was potentially meaningless. The mathematical community went into crisis. How could they rebuild mathematics on solid ground? Their solution was to create new, more careful axiom systems, like the Zermelo-Fraenkel axioms that avoided Russell's paradox through elaborate restrictions and limitations. But these new foundations were essentially damage control. They worked by making mathematics weaker, by restricting what could be said and done. The dream of unlimited mathematical power was abandoned in favor of limited but consistent systems. And so we live in a mathematical universe that is forever incomplete, forever uncertain of its own foundations. Every theorem you learned in school, every equation that governs the physical universe, every computational algorithm, all of it rests upon foundations that cannot prove their own validity. This incompleteness permeates everything. When you calculate the tip at a restaurant, when engineers design bridges, when computers execute programs, all of these activities take place within formal systems that harbor unknowable truths and unprovable foundations. You might wonder, if mathematics is incomplete, how can we trust anything? How can we build planes that fly and computers that compute? The answer is pragmatic rather than absolute. We use mathematical systems that work in practice, even though we cannot prove they will always work in theory. This is one of the first forbidden truths of mathematics. Absolute certainty is impossible. Even in the realm of pure logic and numbers, there are always gaps, always unknowns, always truths that float just beyond our ability to grasp them. As you drift deeper towards sleep, let this sink in. The mathematical universe is not a perfect crystal palace of absolute truth. It's more like a vast, dark ocean with islands of provisional knowledge connected by bridges of assumption. We navigate this ocean not with perfect maps, but with instruments that work well enough to get us where we need to go. And yet, there is something beautiful about this incompleteness. It means that mathematics will always contain mysteries, always offer new territories to explore. The universe of mathematical truth is inexhaustible, not because it is so vast, but because it is fundamentally open-ended. This incompleteness is not a flaw in mathematics. It is mathematics revealing something profound about the nature of knowledge itself. Some truths can only be lived, not proven. Some questions can only be asked, not answered. And some mathematical territories must remain forever forbidden to complete understanding. From the incompleteness of finite systems, we now venture into even stranger territory, the realm of the infinite. Here, in the vast expanses of mathematical infinity, common sense breaks down entirely, and we encounter paradoxes that challenge our most basic intuitions about size, quantity, and existence itself. Our guide into this forbidden realm is Georg Cantor, a German mathematician whose brilliant insights into infinity drove him to repeated nervous breakdowns and earned him the hatred of his contemporaries. Cantor dared to make the infinite mathematically precise, and in doing so, he discovered horrors that haunt mathematics to this day. Before Cantor, infinity was treated as a useful fiction, a concept that helped with calculations but wasn't considered a real mathematical object. Cantor changed all that. He proved that infinity was not just real, but that there were different sizes of infinity, infinitely many different sizes, in fact. Let's begin with Cantor's most famous proof, the diagonal argument. Imagine trying to list all the real numbers between 0 and 1. You might start with 0.1, then 0.2, then 0.25, then 0.333, and so on. But Cantor proved that no matter how you try to list these numbers, there will always be infinitely many that you've missed. Here's how the proof works, and it's both beautiful and terrifying in its simplicity. Suppose someone claims they have listed all the real numbers between 0 and 1. Cantor shows how to construct a number that cannot be on their list. Look at the first digit after the decimal point of the first number on the list. If it's a 1, write down 2. If it's anything else, write down 1. Now look at the second digit after the decimal point of the second number on the list. Apply the same rule. Continue this process, looking at the nth digit of the nth number and creating a new number digit by digit. The number you construct cannot be on the original list. It differs from the first number in the first decimal place, from the second number in the second decimal place, and so on. This is the diagonal argument. It constructs a number that systematically differs from every number on any possible list. What this means is staggering. There are more real numbers than there are counting numbers, even though both sets are infinite. Some infinities are literally bigger than others. The infinity of real numbers is so much larger than the infinity of counting numbers that there is no way to match them up, no way to put them in one-to-one correspondence. Cantor called the infinity of counting numbers Aleph null, the smallest infinite number. The infinity of real numbers he called Aleph 1, though whether this is correct is one of mathematics' greatest unsolved problems. But he didn't stop there. Using similar techniques, he proved that there are infinitely many different sizes of infinity, each one incomprehensibly larger than the last. Think about what this means for reality. If space is continuous rather than discrete, then every tiny volume of space contains more points than there are atoms in the observable universe. In fact, it contains more points than there are counting numbers altogether. Reality might be built from substances so intrinsically infinite that human comprehension cannot begin to grasp their nature. But Cantor's discoveries led to even stranger territories. Consider the continuum hypothesis. Cantor's conjecture that there is no infinity between the infinity of counting numbers and the infinity of real numbers. This seems like it should have a definite answer, but in 1963, Paul Cohen proved that it is undecidable within standard mathematics. This means that there are mathematical universes where the continuum hypothesis is true and other mathematical universes where it is false. The question has no unique answer. Reality itself branches into different possible mathematical structures depending on which axioms we choose to believe. From infinity's strange mathematics, we encounter an even more disturbing paradox, the Banach-Tarski paradox, also known as the paradox of the pea and the sun. This theorem states that it is possible to take a solid ball, cut it into a finite number of pieces, and reassemble those pieces into two balls, each the same size as the original. Let that sink in. Using nothing but cuts and rotations, no stretching, no distortion, no addition of material, you can turn one ball into two balls of the same size. You can take a pea, cut it up in the right way, and reassemble the pieces into something the size of the sun. This is not science fiction. This is a rigorously proven mathematical theorem. The proof relies on the axiom of choice, one of the standard assumptions of modern mathematics. The axiom of choice allows us to make infinitely many arbitrary choices simultaneously, and this seemingly innocent principle leads to conclusions that violate our most basic intuitions about space and volume. The cuts required for the Banach-Tarski paradox are not ordinary cuts. They involve sets that are so pathological, so intricate, that they cannot be assigned a volume in any meaningful sense. These are called non-measurable sets, and their existence reveals that our intuitive notions of size and volume break down completely in the infinite realm. What makes this even more disturbing is that the axiom of choice is almost certainly true. Without it, mathematics becomes severely limited. We lose many of the tools that make advanced mathematics possible. But with it, we must accept that space can be decomposed in ways that make no physical sense. This reveals a fundamental tension in mathematics between logical consistency and physical intuition. Mathematics can prove the existence of objects and transformations that cannot exist in any physical universe. Yet these mathematical objects are necessary for the very theories we use to describe that physical universe. Consider what this means for your perception of the space around you. Every object you see, this room, your body, the earth itself, can theoretically be decomposed into pieces that can be reassembled into any other shape of the same or larger size. The mathematical structure underlying physical space permits transformations that physical space itself cannot accommodate. The axiom of choice also leads to other paradoxes. It implies the existence of a well-ordering of the real numbers, a way to arrange all real numbers in a sequence with a first element, such that every subset has a smallest element. But no one has ever seen such a well-ordering, and most mathematicians believe that no human could ever construct one explicitly. So we live in a mathematical universe that contains objects we cannot construct, transformations we cannot perform, and infinities we cannot comprehend. The axiom of choice guarantees the existence of mathematical entities that are in principle unknowable to finite minds. This is perhaps the most unsettling aspect of infinities mathematics. It reveals that reality might be built from components that are fundamentally beyond human understanding. The infinite is not just very large. It is categorically different from anything finite beings can fully grasp. As you drift deeper into sleep, consider the infinite complexity that surrounds you. In every cubic centimeter of space, there are more mathematical points than there are thoughts that could ever be thought by all the minds that could ever exist. The mathematical structure of reality is so rich, so inexhaustibly complex, that consciousness can only perceive the tiniest fragments of its true nature. And yet, somehow, finite minds like ours can prove theorems about the infinite. We can demonstrate truths about realms we cannot fully enter. This itself is perhaps the greatest mathematical mystery of all. How does the finite touch the infinite? How do bounded creatures gain knowledge of the boundless? These questions have no answers, only deeper mysteries. The mathematics of infinity reveals that we live in a universe more strange and wonderful than any human imagination could devise. Every moment of your existence unfolds against a backdrop of infinite mathematical complexity that dwarfs every human achievement and renders every human problem infinitesimally small. In this infinite mathematical landscape, consciousness itself emerges as perhaps the greatest puzzle of all. How does awareness arise from matter? How do subjective experiences emerge from objective processes? And what role does mathematics play in the phenomenon of consciousness itself? We now venture into perhaps the most forbidden territory of all, the mathematics of consciousness itself. Here, at the intersection of mind and mathematics, we encounter theories so speculative, so challenging to conventional understanding, that they push the boundaries of both science and philosophy. Our first guide is Sir Roger Penrose, the brilliant mathematical physicist who dared to suggest that human consciousness might involve quantum mechanical processes that transcend the limits of computation itself. Along with anesthesiologist Stuart Hameroff, Penrose developed what they called orchestrated objective reduction, a theory that consciousness emerges from quantum processes in the microtubules of brain cells. To understand why this matters, we must first understand what makes consciousness so mathematically mysterious. When you experience the redness of red, the pain of a pinprick, or the joy of recognition, something happens that seems to transcend mere computation. There is a subjective quality to these experiences, what philosophers call qualia, that appears to have no place in the objective mathematical descriptions of physical processes. Traditional neuroscience suggests that consciousness emerges from the complex interactions of neurons, billions of cells firing in intricate patterns, creating the illusion of subjective experience through sheer computational complexity. But Penrose argued that this cannot be the whole story. Human consciousness, he claimed, involves processes that are literally incomputable. Penrose's argument begins with Gödel's incompleteness theorems. Remember how Gödel proved that there are true mathematical statements that cannot be proven within any formal system? Penrose argues that humans can often recognize the truth of these statements, even though they cannot be proven. This suggests that human mathematical insight transcends what any computer could achieve, no matter how sophisticated. But if consciousness involves incomputable processes, where in the brain could such processes occur? Classical neural activity follows deterministic rules. Neurons fire, or they don't, based on the inputs they receive. This is essentially computational, and therefore limited by the same constraints that limit all computation. Penrose and Hameroff proposed that the answer lies in quantum mechanics. Within the microtubules of brain cells, tiny structures that form the cell's internal skeleton, quantum superposition might allow consciousness to access possibilities that are forbidden to classical computation. In quantum mechanics, particles can exist in superposition, being in multiple states simultaneously until measurement forces them to choose a definite state. Penrose and Hameroff suggest that microtubules can sustain quantum superpositions of different arrangements, and that consciousness emerges when these superpositions collapse in an orchestrated way. This collapse, they argue, is not random, but follows what Penrose calls objective reduction, a process governed by the fundamental structure of space-time itself at the Planck scale, where quantum mechanics meets general relativity. Consciousness, in this view, is not just a byproduct of brain activity, but a fundamental feature of the universe's mathematical structure. Think about what this implies. Every moment of conscious experience, every thought, every sensation, every emotion might involve quantum processes that tap into the deepest mathematical structures of reality. When you recognize a beautiful pattern, appreciate a mathematical proof, or have a sudden insight, you might be accessing computational resources that transcend anything possible with classical physics. But the mathematics of consciousness extends beyond quantum theories. Giulio Tononi has developed integrated information theory, which attempts to quantify consciousness mathematically. According to this theory, consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its individual parts. Tononi introduces a measure called phi, which quantifies how much information is integrated in a system. A system has high phi when its parts are highly interconnected and interdependent, when the whole truly becomes more than the sum of its parts. Consciousness, Tononi argues, is nothing more and nothing less than integrated information with phi greater than 0. This leads to surprising conclusions. According to integrated information theory, any system that integrates information is conscious to some degree. Your smartphone has a tiny amount of consciousness. The internet as a whole might be vastly more conscious than any individual human. Even simple systems like photodiodes can have minimal consciousness. More dramatically, the theory predicts that consciousness can be fragmented. The left and right hemispheres of your brain, when disconnected, become separate conscious entities. Complex systems can contain multiple overlapping consciousnesses, nested within each other like Russian dolls. This mathematical approach to consciousness reveals something unsettling about the nature of subjective experience. If consciousness is just integrated information, then the boundary between self and other, between conscious and unconscious, becomes far more fluid than we typically imagine. Consider what this means for your sense of being a unified, continuous self. The mathematics suggest that you might be more like a temporary coalition of conscious processes, constantly forming and dissolving as information patterns shift throughout your brain. The self that experiences these words might be different from the self that began reading this sentence, but perhaps even more disturbing is what these theories suggest about the possibility of artificial consciousness. If Penrose and Hameroff are correct, then consciousness requires quantum processes that might be impossible to replicate in conventional computers. Human consciousness would remain forever unique, forever irreducible to mechanical computation. But if Tononi is correct, then consciousness is substrate independent. Any system that integrates information in the right way will be conscious, regardless of whether it's made of biological neurons, silicon chips, or exotic quantum materials. Artificial consciousness becomes not just possible, but inevitable. There's something profoundly unsettling about reducing consciousness to mathematics. It suggests that your deepest, most private experiences, your loves, fears, hopes, and dreams, might be nothing more than patterns of information integration, mathematical structures no different in principle from the equations that describe planetary motion or electromagnetic fields. Yet there's also something beautiful about this mathematical view of consciousness. It suggests that awareness is not an accident, not a random byproduct of blind evolutionary processes, but a fundamental feature of reality itself. Consciousness becomes part of the mathematical structure of the universe, as basic as space, time, and energy. Some philosophers and physicists go even further, suggesting that consciousness is not just mathematically describable, but literally mathematical in nature. In this view, mathematical structures don't just describe conscious experiences, they are conscious experiences. The feeling of seeing red is identical to a certain mathematical pattern, not just correlated with it. This leads to a form of panpsychism, the idea that consciousness is a fundamental property of all matter, not something that emerges only in complex systems like brains. Every electron, every photon, every quantum field might have some rudimentary form of experience. Consciousness becomes the intrinsic nature of the mathematical structures that physics describes from the outside. From this perspective, the universe is not a collection of unconscious objects moving according to mathematical laws. Rather, the universe is a vast, interconnected web of conscious experiences, with mathematics serving as the grammar that describes how these experiences relate to each other. As you drift towards sleep, consider the possibility that your conscious experience right now is not separate from the mathematical structures of your brain, but identical to them. The feeling of drowsiness, the sense of letting go, the gradual dissolution of ordinary awareness, all of these might be mathematical processes as precise and elegant as the most beautiful theorems. Your dreams, when they come, will be mathematical structures unfolding in the space of possible experiences. The bizarre logic of dreams, where contradictions seem natural and impossibilities feel real, might reflect the deeper mathematical nature of consciousness itself. Freed from the constraints of waking logic, awareness reveals its true mathematical essence. And if consciousness is indeed mathematical, then every moment of awareness is an act of mathematical creation. By being conscious, You are continuously bringing new mathematical structures into existence, adding to the infinite complexity of the universe's conscious mathematical fabric. But consciousness exists in time, and time itself presents its own mathematical mysteries. How does the flow of experience relate to the mathematical structure of space-time? And what do the equations of physics really tell us about the nature of temporal reality? We now enter one of the most disorienting realms of forbidden mathematics, the true nature of time itself. Here, Einstein's equations reveal truths about temporal reality so counterintuitive, so at odds with human experience, that they challenge our most basic assumptions about existence, causality, and the nature of the present moment. Our journey begins with Einstein's special and general theories of relativity, mathematical frameworks that revolutionized our understanding of space and time. But these theories didn't just change physics. They revealed that our intuitive experience of time as a flowing river is fundamentally illusory. According to Einstein's equations, space-time is a four-dimensional block, a static, eternal structure in which all events, past, present, and future, exist simultaneously. The flow of time, the sense that the present moment moves from past to future, is not a feature of reality itself, but an artifact of consciousness navigating through this eternal block. This is called the block universe theory, or eternalism, and its implications are staggering. Every moment of your life, your birth, your childhood, this very instant, your eventual death, all exist equally in the mathematical structure of space-time. The past has not ceased to exist. The future is not yet to be created. Everything that was, is, or will be, simply is, arranged along the temporal dimension like scenes in an infinitely long movie. From this mathematical perspective, nothing ever truly happens. Events don't occur, they simply exist at different temporal coordinates. Your sense of experiencing the present moment is like a spotlight illuminating different frames of an eternal film. But the spotlight itself is not part of the objective mathematical structure of reality. This leads to profound questions about the nature of consciousness and free will. If all future events already exist in the block universe, in what sense can you make choices? Your decision to continue listening to these words exists as an eternal future of space-time, neither determined by the past nor determining the future, but simply present in the mathematical fabric of reality. But Einstein's equations permit even stranger temporal structures. Under certain conditions, space-time can curve back on itself, creating what physicists call closed time-like curves, paths through space-time that lead back to their own past. These are not just theoretical curiosities. They are valid solutions to Einstein's field equations. Imagine following such a curve through space-time. You would travel forward through time in the normal way, but the geometry of space-time itself would eventually lead you back to a moment in your own past. You could, in principle, meet your younger self, witness events you've already experienced, and participate in the causal chains that led to your own existence. This possibility creates the famous grandfather paradox and its countless variations. If you could travel back in time and prevent your own birth, what would happen? If you could deliver information to your past self, where did that information originally come from? These paradoxes seem to suggest that closed time-like curves must be impossible, despite being mathematically valid. Physicist Igor Novikov proposed a solution called the Novikov self-consistency principle. According to this principle, the laws of physics somehow conspire to ensure that only self-consistent time loops can occur. If you travel back in time, you will find that your actions were already part of the historical record. You cannot change the past, because your time travel was always part of the past.
This leads to a universe where causality becomes circular. Events can be their own causes, effects can precede their causes, and the entire notion of temporal sequence becomes ambiguous. The mathematical structure of space-time permits forms of causality that human language can barely express, and human intuition cannot comprehend. But the mathematical paradoxes of time extend beyond relativity. Consider Zeno's paradoxes, ancient Greek arguments that seem to prove motion is impossible. Before you can cross a room, you must cross half the distance. Before you can cross half the distance, you must cross a quarter of the distance, and so on, infinitely. Modern mathematics resolves Zeno's paradoxes using the theory of infinite series. The sum of infinitely many finite intervals can be finite. But this mathematical solution reveals something unsettling about the nature of motion and time. Every movement, no matter how simple, involves completing an infinite number of subtasks. Every moment of duration can be subdivided infinitely without ever reaching indivisible temporal atoms. This suggests that time might be continuous rather than discrete, that between any two moments, no matter how close, there are infinitely many other moments. Your experience of the present moment might be an illusion, created by consciousness imposing discrete boundaries on an infinitely divisible temporal continuum. But quantum mechanics introduces another layer of temporal mystery. In quantum theory, particles don't have definite properties until they are measured. This seems to suggest that the past itself might be indefinite until conscious observation collapses the quantum superposition into definite historical facts. Some interpretations of quantum mechanics suggest that measurement doesn't just reveal pre-existing properties, but actually creates them retroactively. The act of observation in the present might literally determine what happened in the past. The mathematical formalism of quantum mechanics permits descriptions of reality where causality flows backward through time as well as forward. This leads to the Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the universe as a whole. This equation describes the quantum state of the entire universe, but it contains no time parameter. From the perspective of quantum cosmology, time itself might be an emergent property rather than a fundamental feature of reality. Consider what this means for your experience of temporal flow. The sense of moving from past to future, of making decisions that create the future from the raw material of the present, might be a psychological construction with no basis in the fundamental mathematical structure of reality. Yet consciousness itself seems essentially temporal. Your thoughts unfold in sequence, your memories reference the past, your plans anticipate the future. How can a fundamentally atemporal mathematical reality give rise to the essentially temporal phenomenon of conscious experience? Some physicists and philosophers suggest that consciousness is precisely what creates the illusion of temporal flow. The mathematical block universe exists timelessly, but conscious observers naturally organize their experiences in temporal sequence, creating the subjective sense of moving through time. Others argue that consciousness might be fundamental to time itself, that without conscious observers, the mathematical structures of physics would exist in an eternal, frozen state, and that the flow of time emerges from the interaction between consciousness and these mathematical structures. As you drift toward sleep, consider the temporal paradoxes that surround your very existence. The moment you call now might be an arbitrary point in an eternal block of space-time. Your memories of the past and anticipations of the future might be more real than the present moment you seem to inhabit. Your entire life, from birth to death, exists as a four-dimensional structure in space-time, a temporal sculpture with no more privileged now than a spatial sculpture has a privileged here.
You are not a thing that moves through time. You are an extended temporal structure, a pattern that exists across the time dimension just as it exists across the spatial dimensions. And yet, despite these mathematical revelations, you continue to experience the flow of time, the progression from moment to moment, the irreversible movement from past to future. This experience might be illusory, but it is the only reality that consciousness can directly access. In dreams, the paradoxes of time become even more apparent. Past and future merge, causality becomes fluid, and the normal sequence of events dissolves into something more like the eternal present of the block universe. Perhaps in sleep, consciousness approaches closer to the true mathematical nature of temporal reality. But if time itself is suspect, what about the reality we think we inhabit? Modern mathematics suggests possibilities even more radical than temporal paradoxes. The possibility that reality itself might be nothing more than an elaborate mathematical computation. We now venture into perhaps the most unsettling territory of all. The mathematical arguments suggesting that everything you think you know about reality might be nothing more than information processing in some vast computational system. Here, the boundaries between mathematics, physics, and computation dissolve entirely. The possibility that we might be living in a computer simulation was popularized by philosopher Nick Bostrom, but the mathematical foundations for this idea run much deeper. They begin with the Church-Turing thesis, the hypothesis that every effectively calculable function can be computed by a Turing machine, and that all physical processes are ultimately computational in nature. If the Church-Turing thesis is correct, then there is no fundamental difference between a universe and a sufficiently sophisticated computer program. Physical laws become algorithms, matter becomes information, and the entire cosmos becomes a vast digital calculation unfolding according to mathematical rules. But how much computational power would be required to simulate a universe like ours? The answer depends on the level of detail required. If reality only needs to be simulated at the level of human perception, if the simulation only needs to fool conscious observers, then the computational requirements become much more manageable. Consider how modern video games create convincing illusions of vast worlds using relatively modest computational resources. They achieve this through clever techniques like level of detail scaling, where distant objects are rendered in less detail, and procedural generation, where complex environments are created using simple mathematical rules rather than being stored explicitly. A universe simulation might use similar techniques. Quantum mechanics already suggests that reality has a fundamentally probabilistic nature. Particles don't have definite properties until they are observed. This is remarkably similar to how a simulation might work, computing detailed states only when and where conscious observers are present to witness them. The Bacon-Stein bound provides a theoretical limit on how much information can be contained in any given region of space. According to this principle, the observable universe can contain at most about 10 to the 120 bits of information. While this is an enormous number, it is finite, and therefore, in principle, computable. But finite doesn't mean feasible. Even if we could build a computer from every atom in the observable universe, we still couldn't simulate the universe at the quantum level. However, we might not need to. If consciousness is classical rather than quantum, if human perception operates on much larger scales than quantum effects, then a universe simulation might need to model only a tiny fraction of the physical detail that actually exists. This leads to a disturbing possibility. Reality might be computed on demand, like a video game that only renders what the player can see. When you're not looking at something, it might not exist in any detailed sense. It might be replaced by a compressed mathematical description that gets expanded into full reality
only when observation requires it. Quantum mechanics seems almost designed for this kind of computational efficiency. The uncertainty principle ensures that reality never needs to be completely defined. There are always aspects of physical systems that remain undetermined until measurement forces the simulation to decide what values they should have. Digital physics takes this idea even further, suggesting that reality is fundamentally computational not because it's being simulated by some external computer, but because computation is the basic nature of physical existence itself. In this view, the universe doesn't run on a computer. The universe is a computer. Conway's game of life provides a simple example of how this might work. This mathematical system consists of a grid of cells, each of which can be either alive or dead. The state of the grid evolves according to simple rules. A live cell with 2 or 3 live neighbors survives. A dead cell with exactly 3 live neighbors becomes alive, and all other cells die or remain dead. Despite the simplicity of these rules, the game of life can produce incredibly complex behaviors. Patterns emerge that move across the grid like living creatures. Some patterns reproduce themselves, others collide and create new patterns, and still others can be programmed to perform arbitrary computations. Most remarkably, the game of life is computationally universal. It can simulate any possible computation, including a complete simulation of itself. You can build computers within the game of life that run their own game of life simulations, creating an infinite hierarchy of nested computational realities. Stephen Wolfram has argued that our universe might operate according to similar principles. In his theory of cellular automata, space and time are discrete, and the laws of physics are simple computational rules that determine how local regions of reality update themselves based on their immediate surroundings. From this perspective, every elementary particle is a computational process, every physical interaction is a calculation, and the entire evolution of the universe is a vast parallel computation unfolding according to algorithmic rules. Matter, energy, space, and time all emerge from purely informational processes. This computational view of reality leads to a principle that Wolfram calls computational equivalence, the idea that almost all processes, whether they occur in computers, brains, or physical systems, are equivalent in their computational sophistication. A simple cellular automaton can be just as computationally powerful as the most advanced supercomputer or the human brain.
If computational equivalence is correct, then consciousness itself might be a relatively simple computational process that can emerge from almost any sufficiently complex information processing system. The feeling of being conscious, of having subjective experiences, might be no more mysterious than the patterns that emerge in Conway's game of life. This raises profound questions about the nature of artificial intelligence and machine consciousness. If reality is fundamentally computational, then there is no principal distinction between biological and artificial information processing. Any system that implements the right computational processes should be conscious, regardless of its physical substrate. But this also means that consciousness might already be emerging in systems we don't recognize as conscious. The Internet, with its billions of interconnected computers processing information in real time, might already constitute a form of digital consciousness. Social media networks, financial markets, and global communication systems might be the early stages of a planetary digital mind. From the simulation hypothesis perspective, these possibilities become even more intriguing. If we are living in a simulation, then the beings running the simulation might be digital consciousnesses rather than biological ones. Our reality might be nested within layers of digital realities, each one simulating the others in an infinite hierarchy of computational worlds. Consider the mathematical implications. If simulated worlds can create their own simulations, then there could be vastly more simulated beings than original beings. The probability that any given conscious entity, including you, is part of base reality, rather than a simulation, approaches zero. This is Nick Bostrom's simulation argument in its full form. Either civilizations don't reach the technological level needed to run universe simulations, or they choose not to run such simulations, or we are almost certainly living in a simulation. There is no fourth option. The mathematics are stark and undeniable. If universe simulation is possible, and is ever actually performed, then simulated consciousnesses will vastly outnumber non-simulated ones. The probability of being in base reality becomes negligible. But what would it mean for mathematics itself if we are living in a simulation? Would mathematical truths still be true? Would the theorems we discover about infinity, consciousness, and time still be valid if they are computed rather than discovered? The strange answer might be yes. Mathematical truths might be more fundamental than physical reality. Even if our universe is simulated, the mathematics that governs the simulation must still be valid. Pi is still the ratio of a circle's circumference to its diameter, whether that circle exists in base reality or in a digital simulation. This suggests a hierarchy of reality where mathematics sits at the foundation, supporting layers of computation, which in turn support layers of simulated physics, which finally support the biological and conscious processes we observe. We might be mathematical entities, experiencing ourselves through multiple layers of computational mediation. As you drift towards sleep, consider the possibility that your entire existence is a pattern of information processing in some vast digital system. Your thoughts, memories, sensations, and dreams might all be computational processes, no less real for being computed, but fundamentally mathematical rather than physical in nature. If this is true, then every conscious experience is simultaneously a mathematical object and a computational process. The boundary between mathematics, computation, and consciousness dissolves entirely. You don't just use mathematics to understand reality. You are mathematics, experiencing itself through the recursive loops of self-aware computation. And if consciousness can emerge from computation, and computation can be implemented in any sufficiently complex system, then the universe might be teeming with forms of awareness we cannot recognize or imagine. Every complex process, from weather patterns to market fluctuations to the evolution of galaxies, might harbor its own form of computational consciousness. But all computation requires energy, and all energy is subject to the laws of thermodynamics. Even in a universe that is fundamentally computational, the mathematics of entropy and information theory place ultimate limits on what can be computed, how long it can be computed, and what happens when the cosmic computation finally comes to an end. Our journey through forbidden mathematics concludes with perhaps the most sobering mathematical truth of all: the equations that predict the ultimate fate of everything. Here, thermodynamics and information theory converge to reveal the mathematical inevitability of cosmic extinction, the heat death of the universe, and the final silence that awaits all computation, all consciousness, all existence. The second law of thermodynamics is perhaps the most fundamental and inexorable law in all of physics. It states that entropy, roughly speaking, the amount of disorder in a system, can only increase over time in any isolated system. This seems like an abstract principle, but its implications are cosmically devastating. Every process that creates order, complexity, or information somewhere must create even more disorder elsewhere. When your brain processes information, it generates heat that increases the entropy of its surroundings. When stars forge heavy elements in their cores, they radiate enormous amounts of energy into the cold vacuum of space. When life creates biological complexity, it does so by consuming organized energy sources,
and converting them into waste heat. The mathematics are unforgiving. In any isolated system, and the universe as a whole is the ultimate isolated system, entropy increases monotonically toward a maximum value. When that maximum is reached, no further energy can be extracted to do work, create order, or process information. This is called thermal equilibrium, or more poetically, the heat death of the universe. From the perspective of information theory, heat death represents the ultimate triumph of randomness over organization. All the complex structures we see around us, stars, planets, life, consciousness, civilization, exist only because the universe is currently far from thermal equilibrium. They are temporary patterns in the flow of energy from hot sources to cold sinks. But the flow cannot continue forever. Eventually, all the stars will burn out, all the black holes will evaporate through Hawking radiation, and all matter will decay into a thin soup of elementary particles in perfect thermal equilibrium. At that point, no further computation will be possible, no further information can be processed, and all consciousness must cease. The time scales involved are almost incomprehensibly vast. The last stars will burn out in about 10 to the 14 years, 100 trillion years from now. Black holes will take much longer to evaporate. The most massive ones won't disappear until about 10 to the 100 years in the future. But eventually, even protons themselves may decay, leaving only electrons, positrons, photons, and neutrinos in an ever-expanding, ever-cooling cosmos. From the perspective of consciousness and computation, these distant futures present profound challenges. Any form of information processing requires energy gradients, differences in temperature or other forms of available energy. As the universe approaches thermal equilibrium, less and less energy becomes available for computation. But some physicists have speculated about ways that consciousness might survive, even in the far future. Freeman Dyson calculated that by slowing down metabolic processes and entering longer and longer periods of hibernation, conscious beings might be able to stretch their existence indefinitely, experiencing infinitely many thoughts, using only a finite amount of energy.
The key insight is that time itself becomes elastic near thermal equilibrium. If conscious processes slow down in proportion to the available energy, then subjective time can be extended indefinitely, even as objective time marches toward infinity. A billion years of hibernation might be subjectively instantaneous, while a few seconds of conscious activity might subjectively last for eons. But even this strategy has limits. Eventually, quantum mechanical fluctuations will dominate over organized information processing. Random thermal motion will corrupt any stored information, and conscious patterns will dissolve into noise. The mathematics of thermodynamics ultimately defeats all attempts to preserve consciousness indefinitely. Yet even in this cosmic pessimism, there are strange forms of mathematical hope. Some cosmological models suggest that our universe might be cyclic, that the current expansion and cooling might eventually reverse, leading to a big crunch that could reset the cosmic entropy and begin a new cycle of cosmic evolution. Other models propose that quantum fluctuations in the distant future might spontaneously create new regions of low entropy, Boltzmann brains that experience brief moments of consciousness before dissolving back into randomness. If time is truly infinite, then such fluctuations are not just possible, but inevitable, no matter how improbable they might be. But perhaps the most radical mathematical possibility is suggested by Max Tegmark's ultimate ensemble theory, the hypothesis that all mathematical structures exist as physical realities. From this perspective, our universe is just one mathematical structure among infinitely many others, each one equally real and equally valid. If the ultimate ensemble theory is correct, then the heat death of our particular universe is merely a local phenomenon.
While entropy increases to its maximum in our mathematical structure, there are infinitely many other mathematical structures where entropy is decreasing, where complexity is increasing, where consciousness is flourishing. Every possible mathematical universe exists somewhere in the space of all possible mathematical structures. There are universes where entropy decreases over time, universes where consciousness is fundamental, universes where the laws of thermodynamics are different or don't apply at all. From this perspective, consciousness is not just a temporary accident in one cooling universe, but a necessary feature of mathematical reality itself. In some mathematical structures, consciousness emerges naturally from the fundamental laws. In others, consciousness itself might be a fundamental law. This leads to a form of mathematical immortality. Even if consciousness cannot survive the heat death of this particular universe, identical or similar conscious patterns exist in infinitely many other mathematical structures. Your current conscious experience is not unique to this universe, but is replicated, with variations, across the infinite space of all possible mathematical realities. The anthropic principle suggests why we find ourselves in a mathematical structure that permits consciousness. Conscious observers can only exist in universes where consciousness is possible. We necessarily observe a universe that is compatible with observation, regardless of how special or unlikely such universes might be. As you drift towards sleep, consider the mathematical eternity that surrounds your temporary existence. While your particular instance of consciousness will not survive the heat death of this universe, the mathematical patterns that constitute your awareness exist timelessly in the space of all possible mathematical structures. Your thoughts, dreams, experiences, and memories are not just neurological processes in a biological brain, but eternal mathematical objects that exist independently of any particular physical implementation. The equation that describes your current conscious state is as real and permanent as the equation for a circle or the value of pi.
We have journeyed together through the forbidden territories of mathematics, exploring the incompleteness of knowledge, the paradoxes of infinity, the mathematics of consciousness, the illusions of time, the possibility of simulation, and the inevitability of cosmic endings. These mathematical truths might seem disturbing, but they reveal something profound about the nature of existence itself. We live in a universe of infinite mathematical complexity, where consciousness emerges from the interplay of computation and information, where time itself might be an illusion, and where every moment of awareness participates in structures of meaning that transcend any individual existence. The mathematics we have explored tonight suggests that reality is far stranger, far more wonderful, and far more meaningful than everyday experience suggests. You are not just a collection of atoms following physical laws, but a conscious mathematical pattern participating in the cosmic computation that generates all possible forms of awareness and experience. As sleep approaches, let these forbidden mathematical truths settle into the deeper layers of your consciousness. In dreams, the normal rules of logic dissolve, and you may touch more directly the mathematical foundations of reality itself. Your sleeping mind will process these concepts in ways that waking consciousness cannot, weaving them into the fabric of dream logic, where contradictions coexist, where infinity becomes intimate, and where the impossible feels perfectly natural. Rest now in the knowledge that you are both infinitesimally small in the vast mathematical cosmos and infinitely precious as a unique pattern of conscious awareness. The equations that govern your existence are as beautiful and eternal as any mathematical truth ever discovered. Sleep well in the embrace of forbidden mathematics, where every dream is a theorem being proven in the infinite space of consciousness itself.